Hello, good people. Welcome to the next video. We're still in the section about finding area between curves. However, I want to talk about a situation that we saw in one of the previous videos where we had to write two separate integrals because we had a different top and bottom function, right? It actually was the last two videos that we did where, for example, in this situation, this is the top and this is the bottom function. But if I keep moving, at some point it changes. So like right here, it changes. This is still my top, but now I have a new bottom. So I have to write a whole separate integral, one that goes from 0 to 6, and then another one that goes from 6 to 9. And so there's nothing wrong with that, right? Except we are in a time crunch situation here. And so one of the things we could do is, instead of drawing our rectangles this way, what if we drew our rectangles perpendicular to the y-axis, like so? Oh, sorry about that. What if we drew our rectangle slips this way? This way. Well, now my width is not really consistent. And then my height, well, that's kind of weird. And so when we draw them perpendicular to the y-axis, right? And the title is Finding the Area Between Curves with Respect to Y. This little width of the rectangle is now based off of a change in y. So this is delta y, delta y. And the height of the rectangle that's kind of lying down, if you think about it that way, this length is really whatever this is minus whatever this is. And so whenever we draw a rectangle sideways, perpendicular to the y-axis, we think of it this way. We're going to, instead of doing top minus bottom, we're doing right minus left. Because if you look at it this way, we definitely have one function that's always on the right side and one function that's always on the left side. So it doesn't matter, even if I drew a little rectangle slip up here, the right side minus the left side is going to give me the length of the rectangle, and then delta y is going to be the little width of the rectangle. And then I can accumulate rectangles from bottom to top, right? So what is that going to require of me? That's going to require that all my equations are in terms of y. So if I have an equation, I'm going to have to rewrite it in terms of y. So for example, this equation, I'm going to have to square both sides. And now it's x equals y squared. This equation, I'm going to add the 6 over. Now that equals x equals y plus 6. Now I have equations in terms of y. Which one is the left one? Which one is the right one? That's what we're looking for. If I can find my notes that I just made disappear. Oh, Lord. If I can find which is the right and which is the left, then I'm in business, right? Well, the right is the line, so that's going to be y plus 6. And then the left side is this parabola, originally it was a square root, but the sideways parabola, that's going to be y squared. So according to the formula, now instead of doing top minus bottom, we're going to do right function minus left function dy. But what that means is these are y values. So I used to go from starting x to ending x. Now I need to go from starting y to ending y. So when I look at this setup for number 1, this is going to be the integral from the lowest y where the shading is, that would be y0, up to the highest y where the shading is, and those intersect at 3. dy, because that's the width of that little skinny rectangular strip. And then the length of that strip is the top function, the right function, which is y plus 6, minus the left function, which is y squared. This setup right here will find for us the complete area in one integral instead of having to separate them into two integrals because of this boundary issue that we have here, right? So if I'm going from right to left, I can just stack those rectangles here and here and here and take an infinite number of rectangles. And as I take an infinite number of rectangles, well, then it's going to sweep all of this area, stacking from y0 to y3. We're going to get what we want. And that's it. I'm not going to solve this, but this is definitely solvable from here. Actually, it just says set up the integral that allows you to find the area in the first quadrant. We did. I don't need to solve it. So again, if we are drawing rectangles sideways with respect to y or perpendicular to the y-axis, then I need to have my equations in terms of y. I still need to know where my intersection points are, but the intersection points are now y values that I put as the limits of integration, and it's right function minus left function. Okay, so let's see. Can we do the same thing here? I think this is a perfect example where we have to set up this as a y in terms of y. Because if I were to try to do a regular rectangle that's perpendicular to the x-axis, wait, this function is the top and the same function as the bottom? Like, that doesn't make sense. And so we're going to have to think of it as what is my right and what is my left, because my rectangles, if I draw them perpendicular to the y-axis like this, if I draw them horizontal, are going to need the right side minus the left side in order to get that length, right? So what would the setup be? Well, I need to know where the intersection points are. They're here at y equals -2 and here at y equals 1. So I'm stacking this way, so I need to go from the bottom all the way up. Whereas when I was stacking this way, I needed to go from the left all the way to the right. And then which one's which? Well, let's see. First of all, I need to solve for, I don't need to solve for y. It's already solved for y. So I just need to figure out which is which. Well, since this is a sideways parabola, this has to be 3 minus y squared. So that's the right side. That goes first. The right boundary function. And then the left boundary function here is y plus 1. That's the left side. Y plus 1. And we're going to subtract those. Right minus left. And we're going to say dy. This integral will help us find the area that's trapped between the curve. Now you might say, well, wait, how do I go from there? Well, we're not going to go through that, but if you think about it, you combine like terms just like we did before. You take the antiderivative just like you did before, and then you evaluate the top and the bottom limit in the antiderivative and subtract them in that order to get the answer. It's very, very similar. The only difference is my limits of integration are now values of y because I'm going this way and stacking them this way, right? Okay. Whoa, what is this? What is this? An area can be represented by an integral with respect to x or an integral with respect to y. Use a calculator to find the intersection points. We're not going to set this up, but or we're not going to finish it, but I do want to do the respect to y because this is what this video is about. If I do it with respect to y, I'm drawing them this way, right? But I notice that at some point, and that would be at y1, my functions change. And so I need to figure out which is right and which is left. So here's what I know. I know that there's going to have to be two integrals anyway if I'm going to do it with respect to y. The first integral is going to go from 0 to 1. These are y values, so I'm going to put dy. Plus, the second integral is going to go from 1 to whatever this intersection point is. And the thing is, I don't know what this intersection point is, which is why they said to use a calculator to figure this out. So this goes from 1 to whatever that intersection point is. I'm going to call it B. I'm going to call this B. And then I need to figure out which is right and which is left. Okay, in the bottom section, this upside down parabola is the right side, and the upright parabola is the left side. But I need to solve for y. Oh no. So let's see. Solve for y. I'm going to add the x squared to one side. I'm going to subtract the y to the other side, and I get this. And then I'm going to take the square root. So x equals positive or negative square root of 2 minus y. But I want the positive part, where x's are positive. So that means I don't need to worry about the negative part. So this is just positive there. And then for this one, I need to solve for x. So I'm going to take the square root of both sides. So that's positive or negative square root of y equals x minus 1. And then I'm going to add the 1 over. As I do that, I think about, wait, do I need the positive square root of y or the negative square root of y? Even after I add 1 here, which one do I need? Well, I need this part. So is that where the square root of y is positive or where the square root of y is negative? Think about it. For example, at this point right here, that's this part of the parabola. And so I need, oh, wait, no, the parabola goes like this, right? So then this is the dividing part. So I might need, I guess I could write it like this. I took the square roots, yes. Okay, so let's see. I know the right side here is square root of 2 minus y. The left side, oh, that's supposed to be green. I'm sorry. The right side is the square root of 2 minus y. And then the left side, that should be 1 minus the square root of y. And I'm just using this point as a guide because if I plug in 1 in here, square root of y, square root of 1 is 1, and 1 minus 1 is 0, and that's going to give me the x-coordinate of this point, which is 0. Okay, I think I got that part. And then on the other section, this is the top part. I'm sorry, this is the right side, and then the left side is the linear function, which I also need to solve for y. So subtract 1, and then divide by 3/2, which is the same thing as multiply by 2/3. And then that's going to be this side right here, which is 2/3 times y minus 1. Okay, I think I got it. I'm just going to set it up, and we're not even going to solve it, but I just want to make sure that we see that we can get very complicated very quickly. And maybe in this example, doing it with respect to y was not the thing to do. Maybe it was going to be easier to do the rectangle standing up vertical. But since this video was specifically about with respect to y, that's why I did it this way. So from 0 to 1, from y value 0 to y value 1, this is the right side, minus this is the left side. And then from 1 to 2, oh, not 1 to 2, 1 to b, this is the right side still. And then minus this is the left side, which was 2/3. Let me do it in this color since I wrote it in that color. 2/3 y minus 1 dy. The only thing we didn't find was b, but in order to figure that out, I would graph the upside down parabola, 2 minus x squared. I would graph the linear function. Wherever I see the intersection point, that would be the number here. And then I would have everything set up. The moral of the story here is we're going to be playing with these where sometimes it's more convenient to do it one way than it is the other way. And we just don't know until we see the situation, whether maybe doing it horizontal rectangular strips might be easier than doing vertical, perpendicular to the x-axis, vertical rectangular strips. And so that's going to be our work, is we're going to practice to see which method is the most convenient. But I want you to know that it is possible to find areas not just with rectangles standing up, but with rectangles being horizontal. And that's what 8.5 is all about.